Stochastic this afternoon. So it's my pleasure to introduce Andrey Dorogovtsev from Kiev, who will talk about stochastic calculus for flows with singularities.
Thank you very much. First of all, I have to thank to organizers, but Zdislav now is absent, and I already thanked him. Let me go to the subject of my talk. Subject of my talk is the interacting system of Brownian particles on the real line. For such system, I will consider the questions like Kirsanov type theorem, large deviations, Clark representation, flow properties, and local asymptotics. Why we choose such questions? The first reason is that the knowledge about mentioned properties gives us the knowledge about the structure of the system and about its behavior. The second reason is following. Usually we think about the stochastic differential equation or about the flow which is generated by the stochastic differential equation like some subject which can be obtained from the noise by some mapping, like Ito map for usual stochastic differential equation. Then, of course, all these mentioned equations became to be equation about the properties of this Ito map. And everybody can say that if we have a large deviation in Gaussian stuff, then by the contraction principle we can get the large deviation for solution of the stochastic differential equation and so on. But it occurs sometimes that we can have such a system of interacting particles which contains a singular interaction, so we cannot have a good Ito map at all. Actually, this one reason. The second reason is that, for example, when we study flow properties, it is well known, and as far as I know, Professor Yves Lejean make a talk here in the beginning of April. It is well known that sometimes flow related to the interacting Brownian particles does not contain at all a linear Gaussian component. So we have to do some additional work to understand what does it mean now, Krylov-Vereshchnikov expansion and so on. From this point of view, I want to present in my talk some, in my opinion, new tools to investigate the flows of interacting Brownian particles and to consider some results which you can obtain in mentioned direction. Let's go to the tools. What I will consider? I will consider the finite total time of free motion in the system of interacting Brownian particles. I will explain what does it mean. Roughly speaking, it means the total time which spends every particle before to meet some other particle in our system. Then we will see the new notion of quadratic entropy related to the total volume of randomness in our system. Then I will consider Itovian representation for additive and multiplicative white noise functionals. Why I do this? Because we will see that Krylov-Vereshchnikov expansion actually is a purely algebraic construction which does not involve any Lie algebra related to the vector fields or something like this. So this is a tool, this is a tool, and now let's go to the main object which we will study. We will study the system of the random processes on the real line. This process is starting from every point u, and for fixed point this is a Brownian martingale with respect to the common filtration which start from u, and I will suppose that they have a following property. So they keep the order during their motion. The examples of such system can be obtained from smooth stochastic differential equation. For example, if we consider the Wiener sheet on the such product and consider such stochastic differential equation where this function phi is sufficiently smooth and satisfies such condition, then what we will get? We will get the usual stochastic flow. So we will have the required property of ordering, and also we will get that for every point u, this is a Wiener process, because it is a continuous martingale with a characteristic equal to t. Maybe Peter Kotelenets became in the middle of 90s to consider intensively such kind of equations. And here is exactly opposite system. This is Ratia flow. Here we have such property. Our particles are independent up to the meeting, then they then stick and move together as one Brownian particle. From the point of view of martingale characterization, you can see that the joint characteristic is has such derivative. It is equal to 0 up to the moment of the meeting. Now let's see more precisely on this system of the processes, and we can understand that these are not jointly Gaussian processes, and that we have here only some small pieces of independent Wiener processes. So to discuss this system, let us consider the total length of these three pieces. It must be emphasized that the particles here starts from every point of the line. So,
can you go back?
Yeah.
So it's 0 up until they meet, and then it's 1.
Excuse me?
It's 0 up until they meet. Particles meet, and then it's 1.
I don't understand you.
I mean, your formula seems to say that
yes,
it's 1 only when they meet.
Yes, exactly. And
They're independent and
yes, before this they are independent. They have the zero joint factor. Let us consider such random moments for finite number of the particles. Suppose that we have an interval. Let's make a partition of this interval and take here point and so on, u indicated by n. Then we have here trajectories of Ratia flow, and suppose that we have here some time t, and let us define such random moments. The first random moment is t, so I consider all this trajectory. Next moment can be equal to t, or if we hit this trajectory before the t grade, then this will be a tau u1, exactly as in this definition, and so on. So this is a tau u2, and if we organize the sum of these moments, then we will get the total time of free motion for the system, for this finite system of the particles, which start from the point u0, u1, and so on. Now let us see what happens if we change the partitions, if we consider the arbitrary partition. Then we can prove the following theorem, that suprema under all partition is finite. So the total time of free motion in the radial flow is up to the finite moment of the time, of course, is finite. This is the reason to build such integrals. These integrals, probably everybody can explain the reason why we consider such integral, because these integrals arise in the Kirsanov theorem, for example, and other applications of the stochastic calculus to the functionals from Wiener processes. But here we consider this integral on the pieces of free motion, on these small pieces of trajectories when the particles does not hit other particles. So we have here such sums, and you can see here I put 2 sign of integral, but only 1 sign of differential. It emphasizes that this moment tau u becomes to be small as a second differential, actually. Such integrals exist for example, bounded function A, bound measure function A. And I will use such integrals when considering Kirsanov theorem, large deviation for radial flow. But before go further, let us ask following question: what is the analog of finite total free motion for smoothly correlated flow? Because if we have a smoothly correlated flow, the trajectories of the particles never meet one another, and it seems that this property to have a finite total free motion belongs only to the flows with singular interaction. So we have to reformulate this property in order to include such smooth stochastic flow. We have to do this because of, for example, we can prove the following theorem. If we consider such smooth flow, it is smooth because I take here this function phi epsilon from the Schwarz space of smooth function. Suppose that it again has following property, and that support phi epsilon belongs to this interval. Then it can be proved that endpoint motions of this smooth stochastic flow weakly converge to endpoint motion of a radial flow when epsilon tends to 0 plus. It's interesting from different points of view. First of all, it can be compared with the result of Catalanets and Kurtz about exactly the same problem when we have here not R but RD with D greater or equal to 2. We have the opposite behavior. But in this case, we have also smooth flows which goes to the singular flow. So maybe something must be similar for the smooth and singular flows. What is the analog of this property to have finite total free motion? And I present to you this analog. This is notion of quadratic entropy. Let me begin with the abstract setup. Suppose that we have a real separable Hilbert space and we have a sequence of elements of this space. Let us consider for every element of our sequence orthogonal projection of this element onto orthogonal set here. Then let us define the quadratic entropy of the subset of Hilbert space as follows. This is a suprema under all sequence which belongs to A of such sum. Roughly speaking, the quadratic entropy shows us how rich is the set in Hilbert space in the different directions in the Hilbert space. And now let's see for examples of such sets. It occurs that very closely related to this notion, definition was given by Sudakov in 1964 when he considered the sets in Hilbert space which can be considered as a reproducing kernel for different measures, and he proposed such definition. A belong to H is sigma 2 bounded if the supremum under all orthonormal bases in H of such sum is finite. I created such definition by himself, but Vladimir Bogachev said me that already such definition exists, and I am grateful to him.
Over what? The first
Here, supremum is taken over all orthonormal bases. So, of course, if we have a compact set, then we already know that without to the suprema, such series converge uniformly. But here we have such requirement that first of all we put here suprema on the all set A, and here we put here suprema on the all orthonormal basis. It must, thank you for the question, because it must be emphasized that we can produce such set A in H for which this sum is finite for one basis and infinite for other bases.
Show again the definition of the entropy you gave in the previous slide.
Excuse me?
Yeah, exactly this one.
So what are you?
Just to see the definition.
Oh, okay.
Sorry. So I mean X. Later.
Yeah, what is
no,
the?
doesn't matter.
It's super for which x ends?
Yeah, exactly.
Excuse me?
What set of x ends are you taking to super?
There's arbitrary sequence which lie in A.
Oh.
Arbitrary. Because if you take the sequence in one direction, then due to the presence of this pi, it disappears from some points, some n. Now let's see an example of sigma 2 bounded sets. If Q is Hilbert-Schmidt operator in H, then Q from the ball in our space is sigma 2 bounded. Actually relatively hard theorem of Sudakov says that A is sigma 2 bounded if and only if it can be represented as an image of the sum ball under the included in the image of the sum ball under the Hilbert-Schmidt transformation. The following lemma gives us example of the set which has a finite quadratic entropy. If A is sigma 2 bounded, then quadratic entropy is finite. It must be mentioned that I don't know, I try to prove this, but still I don't know if the backward statement is true. So if it is finite, does A be sigma 2 bounded or not? I don't know. And now let's see what happens. If we have arbitrary flow of Brownian particles on the real line, quadratic entropy of this set, this is a set of random variables with finite second moment, so this is a subset of Hilbert space. This quadratic entropy is finite. And when we have such theorem, we can just recall what does it mean, this quadratic entropy. It can be recalculated in the case of Aratia flow, because in the case of Aratia flow, if we have two independent pieces, of course they are orthogonal. They related to the orthogonal, some orthogonal small parts in the L2 space. So we have for Aratia flow such relation, which gives us the finiteness of this total free motion. So, in my opinion, this quadratic entropy, which corresponds to the total amount of the randomness in the stochastic flow, is the substitution of total free motion for the smooth flow. Now let's go to the Ito-Wiener expansion of additive and multiplicative functional from white noise. I will consider multiplicative functionals. We will see what happens, and it's in my opinion, everybody will understand what happens in additive. In additive case, what is my point here? It is well-known Krylov-Veretennikov expansion for the flow, which is related to the smooth stochastic differential equation. So I will consider one-dimensional case. It does not matter. Plus b xt dwt. I will denote by x u t u belong to R. This is a flow related to this equation, and it is well known that if we take a function from x u t, then it can be expressed as here is a semi-group. This is a probability semi-group related to this equation under Hood coefficients, I consider it, from A from U plus, and here we have to infinity. Here we have multiple Wiener integrals of such kind. Here I will show notation. This is a simplex of case order from 0 to t. Here we have t minus tau 1. Here we have differential operator related to this term. Then again t tau k. Tau k minus 1, b, and so on, and finally tau t1 fu dw tau 1 dw tau k. And initially this expansion was obtained using the Ito formula and iteration process, and was used to get the representation of the conditional expectation of the weak solution of stochastic differential equation. So it seems from the first look that Krylov-Veretennikov expansion is closely related to the stochastic differential equation and to the flow which is generated to the stochastic differential equation.
What is capital D?
Capital A
Capital B.
Capital B, this is a differential operator bu d. This is f prime multiplied by b.
Can you write it down?
Yeah. As I said, it seems that a Krylov-Verikhennikov expansion is a property related to the flow generated by the stochastic differential equation. And when we have no the good smooth coefficients or good flow, we have no this expansion. Also, it seems that it must be obtained using the Ito formula or something like this. But here I want to present you purely algebraic stuff, which also allows us to get the same thing as Krylov-Verikhennikov expansion. Now let us see some general picture. Suppose that Xi is a white noise in H multiplied by L2. Of course, here H can be taken another Hilbert space and so on, but that's for simplicity. Then it is well known that arbitrary alpha, which has second moment and is a functional from psi, is measurable with respect to sigma field generated by Xi, can be expanded in Ito linear series, where here is a simplexes, and we have such property. Now let us define a shift operator. This shift operator usually arises in the Markovian picture, and here it is again a shift along the time variable. I just move the kernels. I move the kernels and consider the integrals instead of 0 plus infinity from t to plus infinity because of just also let us define the such sigma fields which are generated by our noise on the time interval as t. Now let us go for the subject which will substitute for us the stochastic flow. This definition was produced by Skorokhod and considered in his book Random Linear Operators. I just use this norm. A continuous linear map from H to L2 omega pH to the space of square integrable random elements in H is referred to as a strong random linear operator in H. Now, this is a definition of multiplicative functional from the noise Xi. Our family GST of strong random linear operators in H is referred to as a multiplicative functional from Xi if this is usual for fixed S, this is identity operator. We have here multiplicative property, and we have here such property that the shift on H of GST is equal to GS plus H T plus H, and suppose that GST is FST measure. It must be noted that we can have rather different examples of such multiplicative functionals. Let me show you. Of course, the one example which we have to keep in mind is following. Suppose that we have a stochastic differential equation x dx ut is equal, I will put only a stochastic term here, x ut dwt, for example, then it produces a flow x s t u. It will be a solution which starts at the time s from the point u, and we look at this solution at the time t. Then we can consider as a space H, for example, L2R. Suppose that phi again belongs to S in order to avoid some technicalities. And then we can consider GST finally from F from U. This is F from X, S, T, U. If we look at such multiplicative functional, we will get exactly the if we consider the e to Wiener expansion of such functional, we will get exactly the Krylov-Veretiennikoff expansion. But of course, there are many other examples of strong linear random operators, and there are many other examples of such multiplicative functionals. For example, such trivial case when we have G, S, T, some J is equal to E W T minus W S on J. So I give such an example to emphasize that multiplicative functional from the Gaussian white noise can be generated not only moving of the phase variable in the space, but this operator is the Hilbert space. For example, it can be multiplication or something else. Now let's go to the e to Wiener expansion theorem. It appears that under very mild condition, this multiplicative functional has a following expansion, where this of course is expectation, because in the e to Wiener expansion we have the zero term which is equal to the expectation. This is usual, and of course this is a semi-group. But what we have to put here? It occurs that here we have to put such kind of a random generator of our multiplicative functionals. We have to consider such integrals with respect to psi with the element of H, taking such product and consider the usual limiting procedure. Let me show you that in this way, in the case of the flow which is generated by the stochastic differential equation, we will get exactly exactly the same expression. Suppose that we have this flow, then what we obtain if we consider the expectation of G0T Fu multiplied by what? Now this is one-dimensional Wiener noise, white noise, so we have to multiply it by T. And what we will get from this equation, it is not hard to calculate that this is equal 0t expectation f prime from x us and that's all ds or phi x us ds. And it's evident that under some technical conditions on F, we have that if we divided this one, it will go to F prime from U or multiply prime from U. So this exactly the some kind of random generator. Why I insist that this is a purely algebraic result? Because of it can be obtained purely algebraic. Let's see. All what we need, it is define this ito kernels. And these kernels can be defined recursively. I show you what happens with the first kernel, because the zero kernel we already have. Let us suppose that we denote by in such manner the first kernel of ito Wiener expansion. Then what we will have? We will have that a t plus s u tau will be equal from how I can get the relation. I can get it from here, that g t plus s from j 0 t from u is equal g 0 t plus s u. So what we will have? We have to compose the zero and first term of ito Wiener expansion from these two multipliers. Then we will have that here we have ts from a1 t u tau multiply on the indicator that tau is less or equal than t plus a s, I use homogeneity, and here t tau minus t u u tau when tau is on the indicator, the tau is greater than t. All what we need now is to compare these two things and take some substitution, and we will get the first we will get the such expression here. Because of if we take tau equal to t, we will get a1 0 u 0, which is equal operator a u. So if we follow the same manner, we will get the kernels of the second order and so on. From this point of view, this is algebraic result which do not use the structure of these multiplicative functionals as functionals which generated by some flow or something. It must be noted that in the same manner I with my pupil Vladimir Bakun in 2003 we gave the theorem about the representation of additive functional from white noise, and it is published in the probability series application in 2003. Now let's go back to our stochastic flows and consider what we can have from these tools. Here just some remarks, excuse me, that of course if we get J which is generated by stochastic flow in such manner, then we get the Krylov, those theorem gives us Krylov-Veritennikov expansion. We can consider the flow of kernels like in the article Lejean and Raimond about stochastic flows, and we will get the Krylov-Veritennikov representation for this flow of kernels, which already is written in the article Lejean and Raimond. Here is example of other stochastic multiplicative functional which I mentioned to you. This is very simple example, and in this example we of course we get well-known representation of stochastic exponent. Here is it. here you can see in this case operator A is equal to 1. So all these exponents gives us only one exponent, and we have usual representation. Now let's go to the Gersonov theorem for Aratia flow. Suppose that we have not Aratia flow, but we have a flow of coalescing diffusion particles. It means that every particle has a motion with drift A and diffusion 1. And the joint law of the motion is exactly the same. The particles move independently up to the meeting, then stick and move together. Then what we have? We can prove the Gersonov theorem that the distribution of the flow on the fixed time and fixed phase interval is absolutely continuous with respect to the distribution of Aratia flow with such density. Of course, the expression of the density is predictable because when we have a one-winner process and when we have drift, we have the usual Gersonov theorem. But here we consider the sum of all pieces of trajectories, free trajectories, and we apply Gersonov theorem locally for every pieces. Now let's go to the large deviation. We consider large deviation for smooth case and for Aratia flow. So in the smooth case, the picture seems to be usual. We have here this square root from epsilon. We have here white noise. So probably, and phi is smooth. Probably we can use some contraction principle, and after some technical work we can get the large deviation. It occurs exactly, and here is the theorem. Suppose that we have such condition. Actually, in my opinion, it is technical condition. We need it due to our way of proof. There are different approaches to prove the large deviations for complicated object, and here we use the approximation and checking of exponential tightness, and when we check this exponential tightness, we need some additional compactness, and this additional compactness comes from this condition. So, in my opinion, this is a rather technical condition which comes from our way of thinking. The rate function also can be predicted because we have a white noise, so we have a rate function for white noise, and then we just solve the equation and have the rate function. But see what happens if we consider the Aratia flow. First of all, let's note that for Aratia flow we cannot multiply the one trajectory by square root of epsilon, because if we have two trajectories which are stick with one another, then multiply this deviation on square root of epsilon and this, we will get the following picture. They never stick one another, and they will demonstrate the parallel motion here. So the picture will disappear. So my proposition is first of all to consider the epsilon here in time. It is in all consistent with the smooth case, because in the smooth case we can also consider the same approach and get the same result. If we consider such family of flows for Aratia, constructed from Aratia flow, then let us start from such very simple but it occurs very interesting picture. Suppose that W is a Brownian motion in RD. B is a closed subset of Rd, some closed subset. And suppose that we stopped our Brownian motion at the moment when we hit this B. Then consider this family of continuous random functions and ask for large deviations. Here must be make some remark. We have many theorems of such kind. If we have the large deviation here, have a good map, then we have large deviation here. Probably the first result is when this map is continuous. The next group of results is devoted to the such case when this map is continuous with respect to measure related to this object. I insist that here we have not such case, because I can demonstrate an example of such set B when the discontinuities of related map have a positive Wiener measure. Such set B is, roughly speaking, Sierpinski carpet with positive Lebesgue measure. Then by Kakutani criterion we get it, and we have a discontinuous on it. Now we have finally we have a large deviation for this eta, and the large deviation of course must have such rate function where f is such continuous functions which are constant after the moment of the first hitting B, and this rate function is equal to infinity if this integral does not exist or the function does not stop when hitting B. After this, of course, we can prove the LDP for Aratia flow. To do this, we have to take a right metric space. In my opinion, this space can be taken in following way. This is a space of distribution functions with Levy-Prokhorov distance. Why we take such function? Because we remember all our stochastic flow has a property of ordering when u1 is less or equal than u2. So we have such non-decreasing function. Then it can be easily shown that Aratia flow has a modification which is right continuous with respect to spatial variable. And moreover, such distance can be recovered if we have the value of x only in the rational points. This is crucial, because when we have the distance which is recovered from the rational points, then we can apply again general approach when we have a large deviation for the sequences and we have a large deviation for the finite pieces, then we will get a large deviation for all sequence. From here we get such rate function, and this is about the large deviation for Aratia flow. The next step is a Clark representation for functionals from Aratia flow.
Could you maybe draw a picture of some event which would illustrate this large deviation principle?
You see what happens. Maybe. Maybe it will be useful to draw up the function which has a finite value of rate function on it. This interesting. This function has a following kind. Most of all, the constant. And somewhere you have a smooth gluing, gluing, and then again they have some constant behavior. So in the limit we have something like this. By the way, it is interesting to build an examples of such continuous trees with the different properties. And I have some students who get already the picture related to usual coding of super processes and Brownian motion and or Levy processes. So now let's go to Arati, to Clark representation. Why I am looking for Clark representation? Because of, as I mentioned it can be proved. Probably it was firstly proved by Cyril Sohn and then many other authors that Arati flow does not contain a linear Gaussian component. So we have to understand how the filtering related to Arati flow is built. What is the structure of this filtering? And of course, the first attempt is to try to move some Gaussian construction on this case. For example, we have a Clark representation from which we get the martingale representation and so on for Wiener stuff. In this case, we already have seen Hirsanov theorem, so we understand what happens. We will get the Clark representation related to these small pieces. And here is it. So we have such kind of representation. For every square integrate alpha, here we have such a sum, and here we have sequence of starts UN. This is a dense sequence in 0, 1, and we have here this sum, and this is very bad actually representation, because it essentially depends not only on the choice of this UN, it depends on the ordering of this point, how we order it. So I present here this theorem only to emphasize that we can move Gaussian construction up to these small pieces of up to the moment of the sticking. Now,
can be given or are part of the representation?
Excuse me?
The UN are given, or I mean, given UN?
No, UN are fixed.
Are fixed.
Then you will give this, you will have this representation. If you fix another UN, you will
Another one. Yeah.
Now the same can be said about the Fourier-Wiener transform. Again, if we consider such kind of linear combinations of such, this is again analog of the stochastic exponent with respect to Arati flow. Then we will get the tenth subset. It can be proved. Now let's go to Ito-Wiener expansion for functionals from Arati flow. Of course, as I mentioned, there are no linear Gaussian components, but we still can consider Arati flow as a functional from the sequence of independent Brownian motion, started from the rational points. Actually, it must be insisted that we have two different problems. The one is to have Ito-Wiener expansion for multiplicative functional related to Arati flow. In this case, we have to consider not Arati flow, but Arati web, and consider the multiplicative functional. And in this case, let me recall you, we already have the representation for multiplicative functional with this operator A, I wrote it. But in this case, it can be proved that A disappear. We have 0 here, so it coincides with Lejeune consideration in his Lejeune and Raymond article 2004. This linear random generator disappears now. So we cannot apply this here. But we still can consider it as a functional from the sequence of independent Brownian motion starting from every rational points. And then we can still look on the Ito-Wiener expansion. This is not a Krylov-Retenical expansion, but still we can consider it and see what happens. Again, let's start from the very simple Brownian motion, which starts at the point X, and it's stopped when hits the 0. And look at the f. This is a smooth function from W from this stopped Brownian motion. And what we will get? This is usual term. And here we have a term where we have two different semigroups. Of course, this is not very hard result, and everybody can get it, for example, using stochastic exponent, multiplying and checking what is the expectation. But it is useful to write this result in such form, using these two semigroups. The one is a semigroup related to the stopped Brownian motion, and second one is a semigroup killed at 0. For Brownian motion killed at 0. Then we have the following representation. And if we have such representation, then we can understand what happens for endpoint motion for Aratia flow. Because in those cases, the particles hit one another. So we have to consider one semigroup which disappears when some of particles meet one another, and other semigroup which go further. This is the answer. And again, we have such representation. This is expectation, and here is the semigroup which kill the process when it hits some diagonal. And here is a semigroup related to the Aratia endpoint motion. This is a usual differential operator related to Brownian motion. Here is. So in this talk, my point was to propose some tools which can be useful when we consider the system of interacting Brownian motion on the line. System as smooth, we can consider as smooth, and we can consider singular interaction. And in my opinion, these tools can be useful, and I try to demonstrate which results can be obtained. So thank you for attention.
Is there a, you looked at the flows on the line.
Yeah.
Is there an analog for multidimensional?
Yes, some results, for example, for smooth flows, the large deviation, of course, can be moved, and also can be moved the results about the quadratic entropy, but we have to be careful in this case. And about the construction of Aratia flow, there are no a good Aratia flow in 2 dimensions. Of course, we can consider such construction: Aratia flow, Aratia flow, Aratia flow, and so on. So we can make multidimensional Aratia flow in this way, but it is unnatural and is very, very simple. But from this point of view, I have other picture which is following. Let us consider not a point motion, but motion of such balls, and then we can consider singular interaction up to the distance, so some distance d. But mainly this is these are construction for the one-dimensional case.
What are some other questions?
For one-dimensional Brownian motion, if you consider one-dimensional Brownian motion, then you may consider one-dimensional Brownian motion plus a drift. And the two are connected by Girsonov formula. And this is somehow, in some sense, the general case, namely, if you consider any absolutely continuous measure with respect to the Wiener measure, this is basically a Brownian motion plus a drift. Namely, Brownian motion plus a drift are dense this is basically a Brownian motion plus a drift up to smoothness.
Yeah.
Is this the case for Arasha flow as well? I mean, you proved that if you consider Arasha flow of processes that are Brownian motion plus a drift,
yeah.
this is absolutely continuous.
I understand your question. This is a very interesting question, and you know, I thought about it, but see what happens. I try to find this. Here is the density. Here is the form of the density. But how we can carefully prove this theorem and theorem of such sort, such kind? We usually use the following approach. We have some finite dimensional approximation and so on. In this case, we have n-point motion, and then go n to infinity, and then we control the densities and prove the usual condition of the uniform integration of this density. In this case, I can do this, but I can do this using the representation of, using the estimation how two processes with drift meet one another. So I did an estimation on this moment of the heating. But if we have processes which simply are absolutely continuously distributed with respect to Brownian motion, maybe it can be done, such an estimation, but I don't know right now how to do this. So I think about this, but what can be done?
In your case, you only consider the Brownian particle. If you replace your Brownian motion by some Levy process, can you still get some similar result?
The first point is that when Levy process have a big jumps, the particles can change the ordering. From this point of view, we cannot describe the interaction properly. So I don't know. Right now, I don't know how to do this.
I just would like to come back to the first part in which you told about the quadratic entropy.
Mm-hmm.
And you show a theorem in which you say that essentially for any flow of Brownian particle, this quadratic entropy is finite.
Yes. Yes. Here is.
Yeah, yeah. And okay, it's arbitrary. We'll need that. But if you look at the just I want to again come back to the multidimensional problem. If you consider a rational flow in more than one dimension, okay, I would say is less interesting because I mean you are less coalescent. But can you get anything like that, or you may just show that this amount of randomness that you measure is simply not interesting, or you get some infinity. I don't know. I mean, what you get.
Thank you for the question. This property is related on very interesting property of one-dimensional martingales. When we want to estimate the square of the non-negative one-dimensional martingale, which is continuous, we can consider it as a Brownian motion from its characteristic, stop it at some time, and this time is less or equal to moment of the hitting zero by Brownian motion. So we have the estimation. If we come back to the multidimensional case, we have to investigate some analog of this property. So at this time, I don't know. Exactly.
Can you get something which is infinite? I mean, in this entropy.
In one-dimensional case, no. In one-dimensional case, no. No.
All right. If there are no other questions, let's thank the speaker again.